For section 310, we're applying the derivative, again, to construct tangent lines, essentially, but we're interpreting values off the tangent lines as approximations to the curve for which they're tangent to. The linearization of a function f at a, if f is differentiable at a, is a name that we have for the tangent line. The equation of the tangent line, L of x equals f of a plus f prime of a times x minus a, is the same equation of a tangent line we've used previously. And the equation of a tangent line in point-slope form, okay, at a point a, f of a, where the function is differentiable at a, we can write, okay, point-slope form is y minus y1 equals m times x minus x1. And if we're talking about being at the fixed point a, f of a, and if we're talking about the slope is equal to f prime of a, okay, well then let's name the output from our tangent line. We'll name that L. L is a function of an arbitrary input x. So L of x minus f of a is equal to f prime of a times x minus a. Right? That's the point-slope form of the equation for the tangent line. If we call the output of the tangent line L of x and then solve for L of x by adding f of a to the other side, we get this equation right here. Okay, so the tangent line is the linearization of the function f at a, as long as f has a first derivative at a. Okay. Now, the linear approximation of f is an output that we get from the tangent line that is meant to approximate an output that would have come from the original function. Now, the tangent line and the function are not going to equal each other in general away from the fixed point. We take a look at the geometry. If we have a function that is differentiable at some point and we look at the tangent line to the function at that point, well then the tangent line and the function have the same output at that point. If the input is a, the output from the tangent line would be L of a. And f of a is the y value at the same point, because that would be along the function curve itself. But if we move away from the fixed point out to another location, let's say x plus delta x, okay, in this case I've added a positive delta x to move to the right. You could do the same thing by adding a negative delta x to move to the left, right? Subtracting a quantity from the fixed point and find another point over here, a point that is on the tangent line and a point that is on the curve itself. Okay? Well, the point on the tangent line at x plus delta x would be this point right here, and its output, its y value for the output would be L of x plus delta x, right? Because it's coming from the tangent line. But x plus delta x plugged into the function itself, right? That would output the y value at this point right here. So here's the idea. When we're doing a linear approximation, we're trying to get an estimate for what the y value is here. Okay, this is the quantity that we want to know. Okay, but in order to approximate it, we're going to use the y value from the tangent line itself. For a variety of reasons, this might be useful. It might be that it's computationally expensive to evaluate the function f for some input. It might be that it's not even possible for us to compute what the value is there. It could be that we are doing a prediction. Okay, so we'll use the tangent line instead, and the tangent line is relatively easy to evaluate because since it is a linear equation, it's only built up out of the operations of addition, subtraction, multiplication, and division, and that's it. But the function f could be built up out of a whole combination of families of functions, and even up out of functions that we haven't even studied yet in this course. Okay. Now, some things to notice from the geometry of the structure here. First, the value of the y value that comes off of the tangent line and the y value that comes off of the curve in general are going to be different from each other, as we've already stated, and the difference between the two is going to be an error in our approximation. Right? So this difference would be a calculated error. Right? So we can calculate the amount of that error by finding the magnitude of the difference between the two. That is, the absolute value of the difference between these two y values would tell us how large this error is. But we can also get an idea of whether our approximation, the one that comes off the tangent line, is an overestimate or an underestimate of the value on the function by subtracting in the following order. We could take the y value from the tangent line, that would be L of x plus delta x, and subtract from it the y value from the function, f of x plus delta x. So this is going to tell us how large the error is. Okay, this also requires that we actually would know the y value off of the function itself, f of x plus delta x. Okay, so what we're also going to want to do is find a way to, if we don't know what this y value is, would we be able to approximate how large of an error we might expect for our linear approximation, and that's coming up in a moment. Okay, but if we know the actual y value for each of these points, if we subtract the linear approximation minus the actual function value, we'll get how large the error is, and we'll know whether we have an overestimate or underestimate. Notice that in this case, this quantity is going to end up being negative. Okay, right? Because the y value at this point is less than the y value at this point. So this is going to end up being a negative value. The absolute value of that is going to be the magnitude of the error, and because it is negative, it's telling us that our tangent line was below the curve. In other words, we have an underestimate. Another way that we could calculate that value is this way. Notice that dy plus the error is equal to delta y. What is delta y? Well, and what is dy? Okay, dy is called the differential. We remember dy and dx from the Leibniz notation dy over dx, right? dy over dx, okay, is equal to f prime of x. That's the differential operator of the function y equals f of x, right, when the derivative exists. Well, also, we were first introduced to a dy and a dx by comparison to a delta y and a delta x. Now, what were delta y and delta x? If we connect the 2 points on the function itself by the use of a secant line, right? So if I draw in purple here, we have, let's say, a secant line. The slope of that secant line in purple here is the difference quotient delta y over delta x. All right, so the y2 minus y1 over x2 minus x1 for the 2 points on the function itself. Well, dy over dx, right, is equal to the derivative when it exists, and it is calculated by taking the limit as delta x approaches 0 of delta y over delta x. Right? The slope of the tangent line is the limit of the slopes of the secant line. Okay? In other words, we're saying that dy over dx is an approximation to delta y over delta x. In other words, right, the slope of the tangent line is meant to approximate the slope of the secant line. And, of course, that approximation gets better and better as delta x shrinks. Okay? As delta x gets smaller, the slope of the tangent line is going to approach, the slope of the corresponding secant line. Okay? So these are approximations here. dy over dx is approximately delta y over delta x. Well, just as delta x is never actually equal to 0, dx is also never actually equal to 0. Instead, it's considered to be a really, really small incremental change in x. Okay? But we can also, in these cases, geometrically quantify it, right, in this way. We can interpret dy over dx, again, as the slope of the tangent line. Right, f prime of x, that's the slope of the tangent line. And we can geometrically interpret the slope of the tangent line through the use of a slope triangle. For instance, we can choose any 2 points on the line, and we can construct a rise over run triangle. Well, then we can say that the rise on this triangle is what dy represents. The differential dy is the rise in this triangle, vertical change. And the dx is the run, right, the horizontal change in our slope triangle taken from the tangent line. The dy and the dx are the rise and the run from the triangle, okay, that tells us about the slope of the tangent line. So the dy and the dx differentials come from the tangent line. By comparison, the delta y and the delta x come from the slope triangle of the secant line. So that's from the 2 points that are on the function itself. The 2 points that are on the function, okay, if we created a slope triangle for those 2 points, that would be this triangle right here, right? And that triangle has as its base its change in x. That's called delta x, right, when it's with respect to the secant line. Well, notice that delta x is exactly the same as dx, right? The length of this side of the triangle is the same for the tangent line as it is for the secant line. Delta x and dx are the same as each other. But delta y, which is the height of this triangle here, okay, going to the function, delta y is not the same as dy. Right? Now delta y is the change in y between the actual y values from the function, and dy is again the change in the y values along the tangent line. So dy and delta y are not the same as each other, but dx and delta x are the same. And of course, as we apply the limit, as delta x approaches 0, the slope of the tangent line approaches the slope of the secant line, but also dy and delta y, they also approach each other in that limit. Now, what is the actual quantification of delta y? Well, it's the difference in the y values again, right? So delta y in this case, right, is f of x plus delta x minus f of x. It's the change in the y values. Now, what is dy? Well, here's how we can find dy. Since dy over dx equals f prime of x, and dx is not equal to 0, and we have a geometric interpretation for what dx represents, we can multiply dx to the other side of this equation to solve for dy. And now dy, the differential of the function y, is equal to f prime of x times dx. And we can use dy now as an approximation to delta y. So we can approximate the actual change in the y value of the curve. All right, we can approximate that change by using the change in the y value along the tangent line. Now dx, again, is the same as delta x. So if we are told some given precision error in an input measurement, you'll see examples like that. If we're told that that something was measured to within an error of plus or minus some amount, okay, that plus or minus some amount is our delta x. So we have some precision error possibly in the input. Well, then there's going to be some output that could potentially be wrong as well. We'll see that in examples like if we measure the radius of a circle. If we measure the radius of the circle to be 5 inches, but the tool that we use to measure it might allow that there could be an error in our measurement of, let's say, plus or minus 1/10 of an inch. So let's say we thought it was 5 inches in radius, but we could be wrong plus or minus 0.1 of an inch. So it could actually be somewhere between 4.9 and 5.1 inches in radius. Well, if we wanted to then calculate an output from using that radius, like let's say the circumference, okay, of the disk. The circumference is 2 pi times the radius. The circumference depends on the radius. And so then the circumference is going to have an error in it if the radius had an error in it. So that is, if our input variable has some type of possible error in it, then we expect that the output is also going to have some type of an error. And we want to be able to approximate how large of an error we might expect to see then in the output in those cases. And to do that, to approximate how large the error may be, we use the differential. Okay? Because the dy is an approximation for delta y. And delta y is going to tell us how large the difference would be between, let's say in our example, if we thought the radius was 5 inches, but it could have been as much as 5.1 inches, right? Then the actual difference, okay, is no more than the difference between the circumference at 5.1 and the circumference at 5 inches. So we can get our maximum possible error is the difference between the y values on the curve is our delta y, and delta y can be approximated by dy. Okay, and all this is really setting us up so that we can apply these processes in cases where it's actually very difficult or perhaps not even possible to find the actual y value of this point right here. As long as we have differentiability of the curve at the fixed point, we can move out along the tangent line and use a value on the tangent line and know that it is an approximation for whatever value we would have expected to have found, okay, if we could have found it. So differentials are the dx's, the dy's, dt's, dv's, dh's, the terms that are found in the numerator and denominator of our derivatives in the Leibniz notation. Okay, some notes on errors. The actual error can be calculated, again, dy minus delta y. Oh, yep, right, that was leading up to that here earlier, right? So I showed here that, okay, so the error is calculated by the difference between these two y values, but if we take the one off the tangent line minus the one off of the function, then we'll also get that whether that difference is positive or negative is going to tell us whether the tangent line's approximation, the linear approximation, is an overestimate or an underestimate. This is an example. This graph is an example of an underestimate. But another way that we can calculate this error here, okay, is we can take dy and subtract delta y from it. Just notice that if we take dy, this distance right here, and subtract this distance right here, we're going to be left with this distance right here, but in this case we'll have that as a negative quantity. Okay, so that's another way that we can calculate what the error is. The relative error, okay, I mentioned previously, the relative error is if we take what the what the maximum possible error was, which is being approximated oftentimes by dy, if you divide that by what y was equal to at the fixed point, you get a relative error. So that is, you can find the error that you find is what proportion of the quantity you're dealing with. So if we have an error in a measurement of 1,000 miles, that sounds like a large amount. But if that's out of a distance of 500 million miles, well, 1,000 miles is not that big of a proportion of 500 million miles, right? So we have the actual value of the error and then the maximum possible error that we might expect to attain. Okay, but then we have how large is that error with respect to how large the actual size of the quantity is. And then if you turn that relative error into a percentage, right? If you write a relative error as a decimal, move the decimal point 2 decimal places over, put a percentage symbol there, you would get a percentage error instead. Okay. I've included here typed notes, okay, with some other graphs, better graphs on here than I could draw by hand. Describing linearization, linear approximations, some examples that I worked through. Okay. Real quickly, take a look. Find the linearization of the function f of x equals sine x at a equals 0. What does that mean? Linearization is the tangent line. So find the tangent line to this function at that fixed point. Alright, so that means we need the slope of the tangent line. So we take the derivative, we evaluate it at the fixed point. There's the slope of the tangent line, it's equal to 1. Here's the equation of the tangent line, whereby the y value of the tangent line we're calling L of x. So now it's the linearization. Okay, so this is really, again, point slope form, y minus y1 equals m times x minus x1, right, solved for y, where y is called L of x, so everything has a different name in this formula. But it's really the point slope form of the equation of a line. It is the equation of a tangent line. Okay, so you plug in the fixed value a equals 0, right, and we end up with L of x is equal to x. What is that telling us? The tangent line to the sine of x at the point 0, 0, because the sine of 0 is also 0, right? At that point 0, 0, the tangent line would be the line with the equation y equals x. And we're calling that the linearization of the sine of x at 0. So y equals x. So that means that y equals x can be used to approximate the sine of x if we choose values that are close to 0. For example, what is the sine of 0.1? Without going to the calculator, if we wanted to know the sine of 0.1, we could approximate it by using the tangent, okay, the tangent line. The sine of 0.1 is approximately 0.1. Because that's what we found here is that the function itself, f of x equals sine of x, is approximately the same as y equals x, as long as we're close to 0. And 0.1 is close to 0. right? So the tangent line is approximately the same as the curve as long as we are near 0. And since the input is near 0, then it's okay for us to use the tangent line for an approximation. Okay. Now we can find out how large of an error did we get by doing this approximation. Well, the error is found because we know what the actual sine of 0.1 is if we say use the calculator. Note that we're plugging in the input value is a real number, so we should be set in radian mode when we do this. So the sine of 0.1 using the calculator gives us this quantity here. Okay. Now what is the error that we found? Well, the error would be the difference between the linear approximation, 0.1, minus, okay, the actual value. So when we do 0.1 minus 0.099833, we get a very small positive number. And that small positive number represents to us geometrically how far above the curve the y value is on the tangent line. And we know it's above. We know that our approximation 0.1 is an overestimate of the actual value as well, because this difference is positive. Now what if we want to approximate the sine of negative 0.1? Using the tangent line again, in this, for this function at that fixed point, the tangent line is just y equals x. So the sine of negative 0.1 is approximately negative 0.1. Let's see how good of an approximation that was. The calculator says the sine of negative 0.1 radians is negative 0.099833. So again, we got a pretty close approximation here. And if we want to find out, is this an overestimate or an underestimate? Well, if you take this quantity from the tangent line and subtract this quantity, that would be subtracting a negative number, okay? You're going to get this minus this is going to equal a negative number, a small negative value. So we get a small error. That error is negative. So we have an underestimate. Okay. So the next example, find the linearization f of x equals square root of 1 plus x at a equals 0. In other words, that would be useful for us to be able to evaluate quantities that are close to the square root of 1. Because if we plug 0 into this, we would get the square root of 1, which is 1. So this would be useful to approximate values like the square root of 1.05, because that's close to the square root of 1, and square root of 0.98, because that's also close to the square root of 1. Okay, so we'll take a look at another example like that. Let's approximate the square root of 10 using an appropriate function. Okay. Let's suppose that we're trying to approximate a quantity like the square root of 10. Okay. Approximate the square root of 10, for now without a calculator. We know that the calculator is there and it can tell us the square root of 10. Great. Okay. Approximate the square root of 10 with a convenient linear approximation. What would be convenient? Right? Is there a... Okay, we're going to use a function that can tell us the square root of 10, but we're going to evaluate that function at a value that is, let's say, close, that is going to give us a value close to the square root of 10, that is a number that we already know. That's the starting point here. Then determine the error in our approximation to 3 decimal places. We should use a calculator for that. Okay? And is the approximation overestimate or underestimate of the actual value for the square root of 10? Okay? Consider a function that would output the square root of 10. Okay? So I'm going to consider f of x is equal to the square root of x. It's not the only choice we could make here. Another choice, for instance, could be something like g of x is equal to, let's say, g of x is equal to, how about 1 plus x squared? Something like that. Because then what would g of 3 equal? G of 3 would equal the square root of 10. Right? So we could build a function that would conveniently tell us the square root of 10 if we were to evaluate it at some value that is within its domain. So that could do it. Okay, but another function I could choose is this. F of x is equal to the square root of x, and let's choose x is equal to a, the fixed value point, okay, to be a value that we can plug in to find a fixed value. This should be where we know what the y value will be exactly on the function. So I'm going to choose a is equal to 9. Okay. So in that case, then f of a would be the square root of a. Well, that's the square root of 9. That just equals 3. Right? So we already know a convenient output to this function that is quote-unquote near the input that we're really interested in plugging in. Let's take a look at this geometrically. Okay, so square root function maybe sort of curves over like that. All right. X is equal to 9. The output would be y is equal to 3. Okay, so yeah, so this is the function y equals f of x. Okay, which is the square root of x function. Okay, so here's our input value, 9. That's equal to a. And our output, f of a, is equal to 3. Right? It's a value of the output of this function that we know is a convenient number. Okay. But what we want to do now is we want to plug in 10 into our function to find the y value. All right, I should probably exaggerate the curve here, so they don't have an exact graph going on here. Okay, so what we want is to target what is the y value there. Okay, so that is, right, what is going to be f of 10, which is the square root of 10. Okay, that would be the y value right here. Now in order to find it, we're going to use the fact that this function is differentiable at this point. Okay, so we can easily find the derivative here. And we're going to use the tangent line and then we'll take the output on the tangent line right here, okay, and that output, okay, would be L of 10. Okay, that's the y value right there when the input is 10. So here's the coordinates for that point right there. Okay, the difference between these two values, that's going to be the error. We can also see from the picture it looks like because of the curvature of our function, of our square root function, relative to the tangent line here, right, the value we get from the tangent line is going to be an overestimate of the actual value from the curve. Right? So let's find, oh, and then I have another example down here. Okay, let's find the equation of the tangent line. Okay, so L of x, okay, is going to equal f of a plus f prime of a times x minus a. Okay, so what is f of a? Well, f of a is 3. What is f prime of a? Well, let's find out what f prime of x is. F prime of x, if f of x is the square root of x, then f prime of x is 1 over 2 root x. Then using that, f prime of a is going to be 1 over 2 root 9, which is 1 over 6, right? So 1/6. So f prime of a is going to be 1/6. Okay, and then this is times x minus a, but that's x minus 9. What's the value of x that we're going to be using? Now we're saying, now the value of x that we're plugging in is 10. And if we plug in 10, we get 3 plus 1/6 times 10 minus 9. All right, 10 minus 9, but 10 minus 9 is 1. Notice that 1 is equal to delta x. Delta x is equal to 1. And that's also equal to dx, because dx and delta x are the same as each other. All right? The difference between these two values, that's our delta x, and that's also dx. Right? Where dx is the change in x from the slope triangle and the tangent line. Okay, so this can be dx right here. Okay. And delta x is the change in x for the slope triangle from the function itself, right? So for the function, if this is the triangle right here for the function, yeah, then the triangle for the tangent line is that, right? So dx is the same as delta x, which we can read from here is equal to 1. That difference right there, x minus a, was delta x. Okay, and now we can use the output from the tangent line to get our approximation. So we get 3 plus 1/6, right? So 3 and 1/6, okay, which is what? Is 19 over 6. Okay, we can even approximate that with a decimal. Okay, let's do that. 19 over 6. This gives us approximately, let's see, 3.1 and then 6, a repeating 6. Okay, so that's in fact an exact value because I use that bar to represent repeating. But approximately then 3.1, let's say 67. There's to 3 decimal places. Okay, now determine the error in the approximation of 3 decimal places. To determine the actual error, we would actually need to know what the actual value, okay, for the square root of 10 is. Now, the actual error can be found by taking dy minus delta y. And we can calculate dy, and we can calculate delta y as well, okay, if we had the actual value of the function. We've got the value, okay, the value from the tangent line first, so L of 10, and then we can subtract from that the value from the function itself. That would be f of 10. Okay, so that is, do an approximation here, approximately 3.167, that's from the tangent line, minus the square root of 10. And the square root of 10 on the calculator is 3.1623. And the difference between those two values, okay, 3.167 minus the number right there, 3 decimal places of accuracy, okay, is approximately positive 0.00 and then 47, so 0.005. Okay. It's actually 0.0047. Okay. All right, so because this difference is positive, it tells us that our approximation, that is the value we got from the tangent line, was above the y value on the curve itself, because we subtracted it in this order. Y value from the tangent line minus y value on the function itself. It required we knew the actual y value from the function, okay, in order to see if this works. Now what we're going to want to do as well is to be able to, again, approximate what the error could have been, its maximum possible error, by using the differential. And remember that dy and delta y, when would they be equal to each other? When would dy and delta y be sure to be the same as each other geometrically? Well, dy and delta y are going to equal each other, right, as long as these 2 points are at the same y value as each other, and so that would have been back here. So once the tangent line and the curve diverge from each other, dy and delta y are not going to be the same as each other. Okay, but dy can be used to approximate delta y. Okay, so now I want to repeat the procedure above for the square root of 8.5. Same idea. Let's come up with an approximation for the square root of 8.5. Okay, so again, I'm going to let f of x equal the square root of x, and I'm going to choose the fixed value of a to be 9 again. Because again, that's near 8.5, and it's a convenient number to plug into our function. It's easy to find the output. We want to construct the linearization function. All right, L of x. Well, L of x is equal to f of a plus f prime of a times x minus a. Okay. Well, f of a is again going to be the square root of 9, which is 3. F prime of a is again going to be 1 over 2 square root of 9, or 1/6. Okay, and then we get x minus 9. All right, let's simplify this a bit. So we have the linearization is L of x is equal to 3 plus 1/6 times x minus 9. All right, it's a linear equation. It is a tangent line. And if x is equal to 9, okay, then we get that if we evaluate this at 9, what do we get? by the way, L of 9 is just equal to 3, right? And 3 is the same as what F of 9 would have been, right? The square root of 9 is equal to 3. The tangent line and the curve are at the same point for the fixed value. Now we want to use the tangent line to find out what the square root of 8.5 is. So I'm going to say, well, what is L of 8.5? That's 3 plus 1/6 times 8.5 minus 9. Okay. Now what's 8.5 minus 9? Negative 0.5. Well, negative 0.5 is then our delta x. All right. All right, so we go back to the picture. All right, if this is 9, 3, not to scale, then if we look to the left to where we find 8.5, okay, find 8.5, right, this is A right now. This was the fixed value. Okay, then our delta x, okay, our delta x is actually negative. Okay, so we are to the left of the fixed value A. All right, we're trying to find out what this value is going to be off of the curve. Okay, we can see that that is below 3, first of all, right? But we're going to be using the tangent line, the same tangent line we used just up above. Right? So the value off of the tangent line is our approximation, right, for the actual value off of the function. All right, negative 0.5 is the same as negative 1/2. Okay, so this is 3 minus 1 over 12. Okay. Or 2 and 11 twelfths, right? 24 and 11 is what, 35? So 35 twelfths. Okay, let's approximate that with a decimal. 35 over 12. You get 2.91 and a repeated 6. Okay, so that's what it's equal to, but approximate it to 3 decimal places is 2.917. So that's the value using the tangent line. That is our linear approximation. All right, now the actual error, okay, is dy minus delta y, but is also found by doing by finding L of 8.5 and subtracting f of 8.5, and for that we need to know what the square root of 8.5 is to 3 decimal places to better accuracy. Okay. Now we can improve accuracy, as you'll see in your future course. You can improve the accuracy of these results by using higher degree polynomials, that is Taylor polynomials, okay, because it'll better approximate the function locally if you do that. So if we extended this idea of using a tangent line to the idea of using a tangent parabola, for instance, we would get an even better approximation. So L of 8.5 was approximately 2.917, and the square root of 8.5 taken from the calculator, that is approximately 2.915, and then it goes to a 4. So I'm going to approximate. Okay, you know what, I'm going to do better than this. 2.9167. I'm going to go an extra decimal place of accuracy there. Minus 2.915, and then it goes 47. So 55. Okay, 2.9167 minus 2.9155. Okay. So I get that this is approximately 0.0012. Okay, so to 3 decimal places of accuracy, 0.001. Okay. And again, we have that our actual error is positive, indicating that this was an overestimate. Okay, again, because of the curvature here, because of how this is curving over, we call this concave down, as we'll see in a couple sections more in depth. Because this is curving over like this, right, then the tangent line is above the function. Okay, so we get an overestimate. And I neglected to write that down above as well, because this is a positive quantity here, and we can see it also from the picture there. This is also going to be an overestimate. Sorry about that. Okay, we have an overestimate here. Okay, so now let's take a further look into differentials. All right, we said that the differential dy is equal to f prime of x dx. Recall that dy over dx equals f prime of x, right, when the derivative exists. Okay. So find the differential for each function. A little bit of practice on finding a differential. So that's essentially find the derivative of the function with respect to the input variable, but then separate the differentials from each other. Right, so move the denominator's differential over to the other side. Right, so you want dy. In this case, we have y as a function of u, so you want to find dy with respect to u. So dy equals f prime of u times du. Okay, so we do need the derivative of this expression with respect to u, so you can use the quotient rule and simplify that. Okay, but remember to write your answer for differentials. Okay, you have a differential on the left and a differential on the right. So we have dy is equal to the derivative times du. Similarly over here, we want to find dy with respect to theta. So dy d theta is equal to the derivative of this function with respect to theta. So we use the product rule there. Well, then dy is equal to the derivative of this times d theta. And that's finding a differential. Harder than that would be applying the differential. Take a look at a couple of examples whereby we use the differential. Okay? And here's one. Use differentials to approximate the volume of a spherical shell of average radius, r equals 1 meter, and thickness delta r equals 0.5 centimeters. Okay, so what we want is the volume of this shell out here. So a sphere is an empty ball, right? So the interior of this is empty, it's hollow. And we have a shell on the outside that's a thickness of 0.5 centimeters. So there's an outer radius, that is, there's an outer sphere, and then there's an inner radius for an inner sphere. If we take the volume of the outer sphere and subtract the volume of the inner sphere, that difference would be the volume of the shell, the amount of material that would make up that shell. And we can calculate that algebraically, right, as a delta V, because it is a change in outputs, a difference in y values, where the y value would be the volume of a sphere. Okay, so what are some elements we need here? We need the volume of a sphere, the formula for volume of a sphere. We know it in terms of radius, V of r. So the volume of a sphere is 4/3 pi r cubed. There's the volume of a sphere. We need that. What else? We're given that the shell has an average radius of 1 meter, but the thickness of the shell is 0.5 centimeters. Okay, so we need these units to match. So we either need to convert meters to centimeters or centimeters to meters, so that we have the same units. Let's convert meters to centimeters. So 100 centimeters is the average radius of the shell. What do we mean by average radius? So let's say that the outer shell and the inner shell, if we add it together, those two radii, and divide it by 2, we'd get 100 centimeters. And the thickness is 0.5 centimeters. So let's say the outer radius is 100 plus 0.25 centimeters. All right, that's the outer radius. So 100.25 centimeters for the outer radius, r sub o. I've called it here. And the inner radius is 100 minus 0.25, right? Then the average of those two radii would be 100 centimeters, and the thickness is 0.5 centimeters. Well, if we use those, the outer radius and the inner radius, we could calculate then the actual volume of the shell with a delta V, right? Because it is the volume with the outer radius minus the volume with the inner radius, using the formula for the volume of a sphere. So just to demonstrate that we could do it that way to find the actual volume, and that's what I calculate out to as many decimal places as I could get from the calculator. Okay, so part of the purpose here of us doing this exercise is we can demonstrate that the power in the calculus is that we can, by using the calculus, we can reduce the amount of computations maybe that we would need to do. Okay. And another purpose would be if the actual calculation was either very expensive to do, so too challenging to do, or if it was even not possible to do, then we would want to rely on the calculus and trust that the approximation that we get with the calculus is going to be sufficient for what it is we're going to be doing. And we can see how good the answer is going to be here. So how do we use differentials? Well, delta V is approximated by dV. So I have dV. That should be a capital V there, an uppercase V. Okay. dV is an approximation for delta V. So let's use dV. What is dV? Well, because V is a function of R, we can find dV dr. That's the derivative of this, V prime of R. So dV is V prime of R times dr. dV is V prime R dr. So what's V prime of R? By the power rule, we get 4 pi r squared. So dV is 4 pi r squared dr. Okay, so now we have dV, and again, dV is an approximation for delta V. So we can find out what delta V is by plugging in an estimate for R and for dr. The estimate for R was 100 centimeters. And the estimate for dr, well, recall that dr and delta r, dx and delta x, those are the same as each other. So we were given a delta r at 0.5, that's what we'll use for our dr. So we plug those quantities in, right? We plug 100 for r and 0.5 for dr, and we get this number, 20,000 pi cubic centimeters. That's our dV using our differential, and it is an approximation for the delta V. And when we calculate that on the calculator to as many decimal places as we get this number here. And look how close the differential output is, right, to the actual output. Okay, it's quite a small error. The actual error can be found by taking our the dV and subtracting delta V. All right, like we said over here. Right, one way to find the actual error, okay, is to take the difference between the y value from the tangent line and the y value from the curve. But another way to find the error would be to take the differential dy and subtracting the delta y from it. Okay, so in this case, we could take our dV, which is this quantity, and subtract delta V. Okay, to answer the question, how large is our error that we got? How much is the difference between these two, but also did we get an overestimate or an underestimate for what the actual volume of that spherical shell was. Okay, so we have 62,831. All those digits are the same, and then the first digit after the decimal point changes. Right, we have a 0.8 here. We had a 0.9 here. Okay, if we round it to the nearest whole number, though, these would be the same. I think that's it for this particular exercise. So one application we had for the differential here was straight up as an approximation to the change in an output. And that's what we could use right here in this example. All right, but another application we have for the differential is, again, as approximating the error. Okay, and that's what we'll use it for in this example. Okay, the circumference of a sphere is measured to be 84 centimeters with a possible error of 0.5 centimeters. That is, we are given that the circumference is 84 centimeters, and the error, a possible error in the circumference is as much as 0.5. So that is to say that the actual circumference of the sphere could be anywhere from 83.5 centimeters to 84.5 centimeters. Okay, depending on the instrument we were using to make the measurement. Okay, that's where we permit that there is this possible error in our measurement. If we use the 84 centimeters to do to evaluate a quantity, in this case we're going to evaluate surface area. If we were to use the circumference of 84 exactly to calculate the surface area, a question would be, how large of an error might we actually have to deal with if it turned out that the actual circumference was 84.5 or 83.5 or 84.1 or 83.92, right, or anything between 83.5 and 84.5, right? If we use this 84 as our input for the circumference, knowing full well that it could be wrong by a certain margin of error, right? Can we estimate how much of an error there could be in the output? Okay. Or a possible bound for it. That's what we're being asked to do. So in order to estimate the maximum error in the calculated surface area, right, we could use a differential. Okay, we want to compare surface area to circumference. That is, can we find a function where the surface area is calculated with respect to circumference? Okay. Well, we have a formula for the surface area of a sphere in terms of radius. This is a formula that I know for surface area of a sphere is S is equal to 4 pi r squared. So we can get surface area as a function of radius. Okay. But we have a measurement of circumference. So what should we do? Well, circumference can also be written as a function of radius. So one thing we could do is we could solve this equation for r. R is equal to c over 2 pi. And then plug that into our surface area function, and we would get surface area in terms of circumference. And that may be an approach you'd like to take. So maybe you'd like to try that right now. You can rewrite surface area in terms of circumference. And then you can continue with this exercise here using surface area in terms of circumference. The way I've chosen to go about it, though, instead, down here in the notes, is to continue with surface area in terms of the radius, and after differentiating, then do the substitutions. Okay, so if you'd like to write this as surface area in terms of circumference right now, okay, you can solve the problem that way, and you should end up with the same answer in the end numerically that I get here. Okay, so the maximum error in the calculated surface area, that is delta S, okay, delta S can be approximated by ds. Right? So we can calculate the surface area at 84 by plugging in an appropriate value of r, for instance, into this formula. Okay? But if the actual circumference was something like 84.3, okay, because that's within the error bounds, 84.3, if that was the actual circumference, then the actual surface area would be different than the surface area we'd be calculating. And if we subtracted one from the other, if we found the difference between those two surface areas, that would be a delta S. And that would be the actual error in our measurement. The delta S can be approximated by the differential ds. How do we find ds? Well, we can take, I'm going to leave this in terms of r for the moment, so I can find ds dr, because that's s prime of r. Take the derivative of this with respect to r, and therefore ds is s prime of r times dr. What's s prime of r? It's going to be, by the power rule, 8 pi r. So ds is 8 pi r dr. Now we want to find ds, okay, we want to find ds under the condition that the circumference is 84 and the dc, or the delta c, is 0.5. Well, delta c is the same as dc. We can find dc, okay, by finding the differential from this equation right here that relates c to r. dc is equal to c prime of r dr, because dc dr is equal to c prime of r. Right? dc dr is equal to the derivative of this. The derivative of this is just 2 pi. So dc equals 2 pi times dr. Right? dc is equal to 2 pi times dr. And then that means that dr is dc over 2 pi. So we can plug that into this differential formula here. And we can plug in that r is equal to c over 2 pi. So we're transforming this, the differential, okay, into a function of c instead of a function of r. Okay, so plug c over 2 pi in, right there. Plug dc over 2 pi in for dr, right there. And then let's simplify this a bit. All right, so 2 times 2 is 4. 4 into 8 goes 2 times. We've got a c in the numerator. We've got a pi divided by pi squared, so a pi left in the denominator in dc. Now, dc is the same as delta c. What is delta c? 0.5. That's the maximum possible error in the input. Okay? So if we plug 0.5 in for dc, and if we plug 84 in for c, then we can evaluate the differential ds. We get that ds is equal to, well, this would be exactly, what, 84 over pi, because 0.5 times 2 is 1, right? So 84 over pi is what ds is. And that comes out to approximately 27 square centimeters, right? It's an approximation of the surface area error, right? So that's why we know we have units in area, right? Centimeters squared. So the maximum error is approximately 27 square centimeters. So for part B, I say, well, what is the relative error? Is this 27 square centimeters, is that a very high amount of error for this problem? Or is it in fact a small amount of error? Well, it depends on how large the error was if we had used 84 centimeters. So that is, let's find out what the surface area would have calculated to, what we would have calculated to be if 84 was the circumference, and then divide our maximum error of 27 by that surface area to see how small it is as a proportion. Okay. So the relative area is found just that way. It's really, the relative error is supposed to be delta S divided by S, but in delta S's place we're using ds, the 27 centimeters squared, or the 84 over pi. Okay? So ds over S. How large is the error of the error bound that we found relative to the size of the surface area that we would get if we used the fixed value, 84? All right, well, surface area in terms of r, s equals 4 pi r squared, but r is equal to c over 2 pi, so the surface area simplifies to c squared over pi. So the surface area for a circumference of 84 is 84 squared over pi. So ds over s is 84 over pi, that was ds, divided by 84 squared over pi. And then that simplifies to 1 over 84, which is approximately the proportion 0.012. So that's the relative error, 0.012. It gives us an idea of how large this error is in the area, this maximum possible error. How large is that relative to the size of the actual shape? And overall, it's not that bad, right? If we turn this into a percentage, this as a percentage is 1.2%. Okay, so there's an application for your differentials. Okay, let's take a look at one more exercise here off of the worksheet. Let's take everything else we've covered here. One more exercise. I'm going to do this one right here. The linear approximation to approximate the cosine of 29 degrees. Okay, approximate the cosine of 29 degrees using linear approximation. Okay, first thing is we should decide on a function that we're going to allow to approximate this value. Now, the approximation value that we're being asked to find, the linear approximation, that's the tangent line. So that's what we want. We want the tangent line to some function, and the tangent line should have a should fix to the function at a point, okay, where they're both equivalent, and it should be close to where the cosine of 29 degrees is. Well, the cosine of 29 degrees is close to, let's say, the cosine of 30 degrees. Okay, it's pretty close to that. It's in that neighborhood. So let's let f of x be the cosine of x, okay, and that implies that I would remind you that x is therefore a real number. When we consider functions like this, f of x equals cosine of x, x is a real number, and that means that x is measured in radians when we input it into here. Okay, so let's let f of x equals cosine of x, okay, where x is a real number, so therefore in radians. Okay, then the fixed value a that we could choose would be a convenient number that we could plug into here so that we could evaluate this function. And 29 degrees is not a convenient value, but 30 degrees is more convenient, okay, because then f of a is the cosine of 30 degrees. The cosine of 30 degrees is root 3 over 2. So that's a quantity that we know. Now, how do we use this function and this fixed value right here in order to find, right, the linear approximation? Right? Linear approximation is L of x. Using L of x, the tangent line. Okay, well, L of x is equal to f of a plus f prime of a times x minus a. Or we call that we want x now to be a real number. Okay, x to be a real number. Okay, now 30 degrees, okay, written in radians would be what? It would be pi over 6 radians, right? Because every 1 degree is 180 radians. Okay. And we're going to want to evaluate our linearization at 29 degrees. Now 29 degrees in radians would be 29 pi over 180, right? Because 1 degree is equal to pi over 180 radians. In other words, 180 degrees is pi radians. So we want to be able to evaluate L of 29 pi over 180. All right, that's what we're going to do. If we take a look at the graph of the cosine function to get an idea for what we're doing here geometrically, perhaps that is helpful. I can get a decent graph here. All right. All right. So if this is not 90 degrees, right? If this would be at pi over 2 right here, okay, we're talking about pi over 6. At pi over 6, which is 30 degrees, we have the fixed point right here. Okay, and the output there is root 3 over 2, right? It's just a sketch. It's not a very good sketch, but it's a sketch. Okay, here's our tangent line. That's our L of x, okay, our linearization. So what we're trying to do here is we're trying to find out, if we know what the output is at 30 degrees, we're trying to find out, well, just to the left of that at 29 degrees, what would have been the output on the function. And we're going to find that by actually finding the output from the tangent line. And notice from this picture, it looks like that our tangent line is going to give us an overestimate to the actual value. Okay. It also looks like delta x is going to be a negative value, and it is. This quantity right here, x minus a, that's our delta x right there. Okay. What is delta x? So delta x is going to be the difference between 29 pi over 180 and pi over 6. Okay, pi over 6 is 30 pi over 180, so this is negative pi over 180. So that's our delta x. Okay? So that we can call this x value right here, we can call that value pi over 6 plus delta x, right? Where delta x is now a negative number, so we're adding a negative number which pushes it to the left. All right, so L of x is equal to, let's see, f of a. We just evaluated f of a, right? F of a is root 3 over 2 plus f prime of a. Now what's going to be f prime of a? Well, we need f prime of x, right? F prime of x is equal to negative sine of x, because f of x was the cosine of x. So f prime of a, that's f prime of the fixed value we're plugging in, which was pi over 6, is negative sine of pi over 6. Negative sine pi over 6 is negative 1/2. So root 3 over 2 plus negative 1/2 times x minus a, against 29 pi over 180 minus pi over 6, which comes out to negative pi over 180. Okay, so let's clean this up a bit. We have root 3 over 2 minus, minus, right? That's going to turn to a plus. Okay, plus pi over 360. Right? So that is L of 29 pi over 180. Right? That's the value that I plugged in here. 29 pi over 180. All right, I think I meant to write here what the linearization was. So L of x is equal to root 3 over 2 plus negative 1/2 times x minus pi over 6, right? That would be the tangent line that we're using, L of x, and then we find the linear approximation by plugging in, right, by plugging in the value, in this case 29 degrees, 29 pi over 180. Okay, so we get this linear approximation right here. Okay, so this should correspond with the value that we have here, right? Root 3 over 2 plus pi over 360, which comes out to approximately 0.875. Okay. So does that correspond to what we interpreted here geometrically? It looked like the value from the tangent line was going to be higher, right, than the value from the actual function, that it was going to be an overestimate, that is. Okay, an overestimate. Okay, well, let's look at what the error is. Okay. First, L of 29 pi over 180 comes out to approximately 0.875. Okay, but the actual value, F of 29 pi over 180, what does that come out to equal? Get that comes out to 0.8746. Okay. I'm going to go out some more decimal places. Let's see all the decimal places we can get from the calculator. So for the linearization, I get 0.8747525. For the actual value from the function, for the cosine of 29 pi over 180, 0.8746197071. Okay, so how accurate were our results? Okay, how many decimal places of accuracy? Right. This is the same, this is the same, this is the same, and this is the same. And then we move over to the next digit, and we have a difference right there. Okay, so in fact, the answer is accurate to 3 decimal places of accuracy. Right? We see that L of 29 pi over 180 is approximately 0.875, but that's also approximately F of 29 pi over 180. So the 3 decimal places, they are the same as each other. What's the amount of the error? The error would be a delta y. Okay, so delta y can be found by taking L of 29 pi over 180 minus F of 29 pi over 180. And remember, this is going to tell us the magnitude of the error, but also whether we have an overestimate or an underestimate. Okay, so if we take this quantity, L, and then we subtract the quantity from F, what do we get? 0.87475205 minus 0.87461977071. So I get that this is approximately 1.323429 times 10 to the negative 4. Okay, so the error is approximately 0.00013. Let's go right there. Okay. Pretty small error though. So in this case, the linear approximation was pretty good. Okay. Checking out the homework. All right. Find a linearization, step-by-step tutorial exercise, a couple more linearizations of function head A. Use L of x in order to approximate these numbers. Right? You have a is equal to 0. That means x is equal to 0. That means the fixed point is close to the square root of 4. Square root of 4 is equal to 2. So this function would be good for evaluating quantities that are close to the square root of 4, right? Because the fixed value is 0 for x, right? You're going to plug in 0 for x, to get the fixed value. Okay, so close to the square root of 4, something like the square root of 3.9. Okay, so you think, what value of x would you plug into f of x when you're evaluating the square root of 3.9? And that value of x could be the value of x that you plug into the L of x linearization, okay, in order to find the linear approximation. So again, approximation for the square root of 3.9, approximation for the square root of 3.99. You can compare those to the actual values that you get from the calculator, but the exercise is not going to the calculator to find out what these are. The exercise is finding the tangent line, okay, in order to come up with an approximation. Okay, choose the right graph of the function and the associated tangent line. Should be able to figure that out from where, the look of this function and where the fixed point is, the shape of the tangent line. Another one like that. finding a differential, dy is equal to y prime times dx. Right? Find the differential. Okay, looking at delta y versus dy, delta x versus dx. Okay, remember delta x and dx are in fact the same as each other. You can find out what delta y is with the difference of actual y's from the function. And dy can be found by using the differential and then inputting the appropriate values. And then sketch a diagram. Okay, a diagram. Remember that the dx and the dy, those come from the slope triangle for the tangent line, and the delta y and delta x come from the slope triangle from the function itself. And then using differentials to estimate the given numbers, like we just did with the cosine of 29 degrees, for example, and the square root of 10. Find an appropriate function that would represent this quantity, an appropriate function and an input value, a fixed input value that is a convenient number to plug in. Okay, so this is not an exercise of plugging this into the calculator and seeing what the calculator tells you this is. It's finding a function f of x that could be used to approximate this. Okay, so that this is in a neighborhood nearby, okay, to some other fixed value that would be a convenient number that you wouldn't need a calculator, okay, to evaluate. Okay, the same for this. And then, well, a couple exercises using differentials in order to estimate maximum error, relative error, percentage error. Okay, so that's it for this section. If there's any questions, you can let me know. Okay, otherwise, good luck on the homework. Take care.